It's kind of funny when you think about it, but atoms are a lot like people. Seriously, they're always interacting, always trying to find some stability, and they're forming all kinds of relationships. So let's dive in and explore the wild world of chemical bonds. Think of it as the original social network, but for atoms.
This quote just nails it, doesn't it? At their core, just like us, atoms are driven to connect, and the type of connection they make, the type of bond, is what determines, well, everything. The properties of the water you drink, the salt on your fries, the air you're breathing, it all comes down to these bonds.
And what's really cool is how well our own relationships map onto the world of chemistry. So think about casual friends. That's kind of like a nonpolar covalent bond. It's a totally equal, balanced partnership. A committed relationship, well, that's more like a polar covalent bond. You're still sharing for sure, but maybe one partner's pulling a little more weight. And marriage? Oh, that can be like a super powerful ionic bond, this intense, almost magnetic attraction between total opposites.
All right, so let's get down to the really fundamental question here. We know atoms form bonds, but why? What's the driving force behind all this? Well, it all boils down to one simple, universal desire: the quest for stability.
I mean, it's the most basic question, right? Why even bother with all this bonding stuff? Why not just hang out solo? The answer, as it turns out, has everything to do with energy.
Think of it like this. You know that feeling after a long day when you just collapse onto the couch? That's your lowest energy state. Well, atoms are constantly trying to do the exact same thing. They're trying to find their comfiest, most relaxed state. And they do that by balancing two key forces. On one hand, you have attraction. The negative electrons of one atom are drawn to the positive nucleus of another. But if they get too close, their positive centers start pushing each other away. It's a delicate dance.
And this dance leads us to something called bond length. You can basically think of it as the perfect amount of personal space for atoms. It's that absolute sweet spot where the attractive pull and the repulsive push perfectly cancel each other out. At that precise distance, the atoms are in their most stable, lowest energy state. Everyone's happy.
So, let's make this real with an actual example. Chlorine. When two chlorine atoms get together to form the chlorine gas we use in pools, they have to find that one perfect bond length to become stable. And we can measure this with just incredible precision. The ideal distance between the centers of two bonded chlorine atoms is just under 2/1000th of a nanometer. It's at that unbelievably tiny, specific distance that they find their stability. And here's the payoff. That negative number means energy has actually been released. The new molecule is way more stable, 239 kilojoules more stable for every mole of them, which is just a big counting number for chemists, than two separate chlorine atoms just floating around. It's a successful, low-stress relationship for sure.
Okay, so let's jump into our first major bond type. We're going to start with covalent bonds, which are all about sharing. But as we all know from our own lives, sharing isn't always a perfect 50-50 deal, is it?
So this is the basic idea. In a covalent bond, you've got electrons that are attracted to both atomic centers, so they just hang out in the space right between them. And that act of sharing is literally the glue that holds the two atoms together.
And this is where it gets really interesting, because just like some friends might put a little more effort into a friendship, some atoms are, well, a little greedier with those shared electrons.
This whole idea is governed by a property we call electronegativity. It's basically just a measure of how strongly an atom can tug on shared electrons in a bond. Some atoms are total electron hogs, while others are a lot more chill about sharing.
This difference in greediness gives us two main types of covalent bonds. Over on the left, you've got nonpolar. The two atoms have about the same strength, so the sharing is perfectly equal and balanced. But on the right, you get a polar bond. Now, it's more like a game of tug-of-war, where one atom is way stronger, pulling those electrons closer. This creates a slightly negative area on its end and leaves the other end slightly positive.
All right, let's switch gears to a totally different kind of relationship. Forget sharing. Ionic bonds are all about a complete and total transfer. It's the classic case of opposites attracting with some serious force. The huge difference here is that word transfer. One atom doesn't just share, it completely gives away an electron, and another atom takes it. This process turns them into ions, atoms that now have a positive or negative charge. And that charge difference creates this incredibly powerful, magnetic-like attraction that forms the bond.
The whole process is actually a pretty simple three-step dance. First, as you see in step 1, An atom, like a metal, which doesn't hold on to its electrons very tightly, just lets one go. Then, in step 2, a non-metal atom swoops in and grabs it. Finally, step 3, the first atom is now positive, the second is negative. Opposites attract, and bam, they lock together in a super strong, super stable bond.
Now here's another thing that makes ionic bonds different. Unlike the sometimes fuzzy sharing in covalent bonds, this is all about clear-cut, distinct positive and negative charges. And because it's so black and white, we can actually calculate the energy of that attraction with some amazing precision.
The strength of this bond is described by what's called Coulomb's law. And don't let the formula scare you. All it's really saying is that the bond energy depends on two really simple things: how strong those positive and negative charges are, and how close together they are. That's it. Stronger charges and a smaller distance mean a much, much stronger bond. So, we've talked about equal sharing, we've talked about unequal sharing, and we've talked about a complete transfer of electrons. But in the real world, chemistry, a lot like human relationships, right, isn't always so perfectly black and white. It's really more of a spectrum.
This chart gives you the big picture. Way over on one end, you've got the perfectly equal sharing of nonpolar bonds. As one atom starts to pull on the electrons a little harder, you move into that middle, polar covalent zone. And if that pull becomes so strong that the electron is basically stolen, you've reached the other end of the spectrum with an ionic bond. So you see, it's not really 3 separate boxes, it's one long continuous spectrum. And these differences in bonding have major real-world consequences. Ionic compounds, like your table salt, are typically hard crystalline solids. They usually dissolve in water, and once they're dissolved, they can conduct electricity. Covalent compounds, like wax or even chlorine gas, tend to be softer. They might be liquids or gases at room temp, and they generally don't dissolve in water or conduct electricity. It all comes back to the polarity of the bonds holding them together.
So let's end on this thought. We use labels like covalent and ionic because they are super useful for predicting how things will behave. But the reality is a beautiful, messy spectrum. It really makes you wonder, doesn't it? At what point does unequal sharing become a complete giveaway? It's one of those questions that reminds us that in chemistry, just like in life, the lines we draw are often just there for our own convenience.